Hey guys, hope you're all doing good and welcome to a new video. So we are going to be picking up from where we left off in the previous video. We ran the no hydro simulation and it ran through successfully. So if I do tail -20 log, it's going to print the last 20 lines of the log file, and you can see that that's how long the simulation took to run. So that's not very long, right? So something like 25 minutes. Now one thing that I did do is I did course on the mesh because when we ran it with a 2 mm base grid, so it had around 200,000 cells and it was taking a lot of time for the no hydro. So what I did is I put in a grid scale of -1, which essentially means that the base grid is like 4 millimeters. So that resulted in a fewer cell count, which I think is around 20,000. So that's why the simulation ran in 25 minutes. If we had set it to 4 mm, then it would have taken more time. So let's take a look at the log file. So the first thing that I typically like to do is I open up the log file from the top and I just read through the first few lines just to make sure that there are no error messages or warning messages. Typically, if there is an error related to the pre-processing stage where you have set up the motion profile or you have flagged the boundaries or regions, then you should be able to track those errors in the first few lines till the calculations start. If you skim through this, you can see that there are no errors or warning messages, and you can see that the calculations have begun. So in order to be thorough, what you can do is you can use the grep tool. So grep -I basically performs a case insensitive search, right? So I can search for warning, or what I can do is I can search for capital warning. It doesn't matter, right? It's doing a case insensitive search, which means lowercase or uppercase doesn't matter. And I can just type in the log file. Basically, I'm searching for the string warning in my log file, and if I hit enter, you can see that there are no warning messages. So the other thing that I like to see is my time step. So one thing you can do is you can type in grep dt log file, and you can continuously see what's your cycle number, what's the current time, and what's the time step being used, and what's the time step limiter, right? So if you remember, Converge uses a dynamic time step, which means it is evaluating several factors which might be a bottleneck for the simulation in terms of the time step size, and then it's going to use the best possible time step so that your simulation runs in a smooth manner, meaning it does not recover or it does not blow up. That's the objective of the dynamic time step. Now in general, you want to see a limiter that's actually reasonable. For example, if you see something like dt_CFL, that's actually a good thing, which means your simulation is being limited by the maximum CFL number that you have provided. That means your simulation has been set up pretty well. If you're getting dt move, that means your simulation is being limited by how much a particular geometry can move. So what does that mean? Well, if you look at this post-processing instance, I have this lobe here, right? Now this is a different post-processing program. Don't worry, you can kind of follow through the same thing in ParaView itself. So here you can see that the lobe is actually rotating, right? Now, so when the lobe rotates, no parts of the 3D lobe should cross more than one computational cell. So that is like a limiter that's been placed in Converge, right? The idea there is quite simple. So say that you have crossed over a cell completely. What do you do to the mass in that particular cell? How do you distribute it? You have to come up with a scheme to do this, which is mass conserving, and which also makes sure that it transfers the momentum in the right direction and other species in the right direction. And hence in Converge 2.3 and previous versions, this constraint is there, right? So is this bad or good? Well, it's not bad. This means that the speed of your simulation is not driven by one of the physics-based quantities like CFL numbers, whereas it's being driven by the geometry. Now, in this case, that's kind of expected, right? Because you are running a no hydro simulations where no CFD equations are being solved, right? So when we actually run a hydrodynamic simulation where we are solving all these equations, only then would we know what the limiter is. But as far as the no hydro simulation is concerned, think about it, right? Now, if your cell is pretty big, meaning if your mesh is really coarse, your computational cell is large, right? Which means I can take a larger time step and I can still be within the same computational cell, right? It's possible. However, if the cell size is very, very small, then there's not a lot of room available for me to move, which means you would still be limited by dt move, but then the time step by which you're limited is going to be extremely small. In this case, the speed at which the rotor is rotating, with a time step of 3.4 e-6, it's able to cross one cell. You can kind of think of it like that. When the cell size is much more smaller, that time step is going to be even more smaller, like 1 e-6 or even smaller, who knows, right? And that is why this particular simulation is going to be quite slow, especially when you start refining the mesh. Alright, so how do the results look like? Well, the no hydro simulation ran through perfectly well, as I said, and here is basically a post-processing of the no hydro simulation. So you can clearly see that the rotors are rotating correctly, and you can see the mesh being created and shown in different views. So here what I've done is I've created a set of cut planes, and you can basically see the mesh motion, and since the mesh is being created every time step, Converge can handle these type of complex geometries very easily. Now, performing no hydro simulations for these type of scenarios is extremely important. Why is that? Well, it helps you understand what type of computational mesh you're getting, and you can kind of think about refinement strategies. So let me stop this and go back to Insight, and let's concentrate on this particular picture because I think this is a great picture. So here your lobe is actually very close to the casing, right? So you can think of this as your smallest flow path in your entire simulation. Now you might have a much more smaller flow path when the lobes are kind of interlocking with each other, but to convey the point that I'm trying to make, I think let's assume that this is the smallest gap available. Now the thing about small gap sizes, you at least want to make sure that you have one entire cell there. Well, how do we make sure? We had talked about something called a cell pairing, right? So for example, this right here is an uncut cell, right? It's a perfect cuboidal cell, and this right here is a cut cell, right? Because it's being cut by the boundaries top and above. Now if the volume of the cut cell is less than 30% of the volume of an entire cell, now if the volume of a cut cell is less than 30% than the volume of an uncut cell, then this cell is going to get paired. Now whom is it going to get paired with? Well, in this particular case, it's most likely going to get paired with this particular cell, because it's basically sharing the maximum area with that particular cell. On the left hand side you have a cell, but this face area, right, is much smaller than this face area. So this cell is going to get paired with this cell. Now what about this cell? Well, that can get paired with this cell again. So in this entire gap you just have one cell. Now in terms of getting the mass flow through this gap, well, this might give a reasonable answer, right? Because mass has to be conserved. So any mass that actually goes from this side has to leave that side, right? So it would basically give you the mass flow rate, but it might actually give you unrealistic velocities, which might affect your torque calculations. So that is why you need to make sure that you have at least an entire cell in this gap, and the way to make sure of that is to refine this particular area. So the systematic way of doing this is to measure this particular gap and then put a cell size accordingly. So let's do that. So how do you measure the gap? Well, we are going to be using a technique called projections. Well, in this case, we just need an approximate measurement. So what I'm going to do is I'm just going to look a location where you can pick 2 points and just kind of calculate the distance. So let me first go to view, and then let me enable the geometry dock. I'm going to go to measure. I'm going to say distance between two vertices, and I'm just going to measure this guy and this guy, right? The alternate way of measuring it could be that you can measure the diameter of the casing, right, by measuring 3 points, and you can measure the distance from this point to the end of the lobe, and once you have the two diameters, you can subtract that and you can get that gap size. But I'm interested in getting an approximate measurement, right? So this right here, let us say that this is the gap size, and let's click on apply. So right, that's about 1.8 millimeters, right? So this is 1.8 millimeters. So then I'm going to just assume that this is 1 millimeter, right? It's probably bigger than that, but let's just play it safe, and we can call it as 1 millimeter. If you want to measure it exactly, then you can use the previous method that I mentioned, where you measure this particular radius and you measure the distance from the center to the casing and you subtract that. So let's go to case setup, and what we're going to do is we're going to go to base grid. We are going to have it at 2 mm, right? And the next thing that I'm going to do is I'm going to go to fixed embedding, and let's add a new embedding, and we are going to be adding it in a boundary, and we are going to be adding it on the left lobe. Now this is going to be permanent, and for embed scale I'm going to say that we need a level of 3. Now let's do the math. So since your base grid is 2 mm and since your scale is 3, so it's going to take 2 mm and divide it by 8. So that's basically 1 by 4 of a millimeter, so that's 0.25 millimeters. Now since our gap size is 1 millimeter, we can be sure that we get 3 to 4 cells. So why am I saying 3 to 4 cells? Well, since the rotor is continuously rotating, right? Now there are certain instances, right? For example, between the rotor tips where the gap might be smaller. If it is smaller, then the number of cells in that tiny gap can change from 4 to 3 or even 2, but it's definitely going to be at least 1 in our case. Alright, so with that being said, the other thing that I'm going to do is I'm going to enable adaptive mesh refinement. Now, in addition to resolving the flow in the gap, we also want to capture gradients in velocity. So I'm going to be enabling the adaptive mesh refinement, and I'm going to add it to region 0. We're going to do it velocity based, and we are going to leave it at the default setting. And I'm going to be saying that, we can expect up to 2 million cells. Now, you might not be able to run this. So try to run it at the maximum resolution your computer permits. So in my case, yes, I think that's 2 million. Let me click on validate. That looks okay. Now, another important thing that you need to take care of is in high speed flows, right? So in these type of situations, the flow velocities can be very high. In that case, in order to make sure that conservation laws are not being broken, we need to make sure that instead of solving just the energy equation, we are solving for total energy as well. So when you typically solve the energy equation, you're basically writing the energy equation in terms of the internal energy. And for low speed flows, this is perfectly fine because contribution that's coming from the velocity component is not a lot. However, if you have very high speed flows with shock waves, then you have high internal energy and also have high velocity. In that case, writing your energy equation in terms of total energy can help prevent conservation issues. So that is why in this particular case, we need to make sure that solve total energy flag is enabled. So let's click on OK. Alright, so with that, my baseline hydrodynamic setup is complete. I'm going to be running the simulations, and once I have post-processed the results, I will get back to you guys. With that, I would like to conclude this video, and I'll see you in the next one. Bye.